So we'll get over empirical and molecular formulas and also combustion analysis. Now, an empirical formula is also referred to as a simple formula. It just shows the simplest whole number ratio of atoms in a compound. For example, when you're talking about hydrogen peroxide, the formula is H2O2. But the empirical formula 2 can go into 2, and so the empirical formula is going to be the simplest formula for this, and that is going to be HO. Okay, this is the empirical formula. It's not an hydroxide. Another example I can give is glucose, which is C6H12O6. This formula is the actual formula for glucose. So the actual formula, which actually shows the number of atoms which are reacting to form a compound, is called the molecular formula. So you know that 6 can go into 6 and into 12. So the simplest formula would be CH2O. So this is showing you the ratio in which carbon, hydrogen, and oxygen are going to react to form this compound. So this is a molecular formula. This is a empirical formula. Molecular formula shows the actual number of atoms that is supposed to react to form a compound. Empirical formula shows the simplest whole number ratio of atoms that are supposed to react to form a compound. Are we okay? Are we moving together? So to talk about combustion analysis itself, whenever you hear of combustion, combustion has to do with burning something. And now when it comes to reaction chemistry, it means reacting something in oxygen. So every time you react a compound in oxygen, it is going to burn or break, and that is combustion. Now, on this topic, we're going to be interested in the combustion of organic compounds. So every time you get an organic compound, let me call it X. Okay, you burn it in oxygen. Every time you burn an organic compound in oxygen, you always produce carbon dioxide and water. This is one reaction that you did also in high school. The combustion of an organic compound produces carbon dioxide and water. So combustion is just reacting something in oxygen. So this is basically the simple definitions. Yes, please. We have a question? Are we together? Paxina, you can go on. Okay, it seems she doesn't want to speak. Okay, so let's start with how do you get to calculate or to find empirical formulas. Now, before we get to in the calculation of empirical formulas, let's say you have got a compound that is made up of sodium. Yes. It should be network. Is it the case with everyone else? You can't get me. Okay. Now, let's say you have got a compound that is made up of sodium. Let's say we have got such a compound, okay, like this one, sodium, hydrogen, and oxygen. Let's say we just have such a compound. I'm not saying it's a true formula, okay, but let's say we have got this compound. And then you've been told that your bone in the body, okay, your bone in the body contains, let's say, 2% hydrogen, right? And then you've been given 10 grams of this compound you are able to see. So the question comes to say, calculate the mass of hydrogen in the bond. So what we have is that in a human body, a bone contains 10 grams of this compound that you're able to see. Now, from that 10 grams, only 2%, okay, is hydrogen, we can say that. Or let me say, let me change the question so that, because the way I'm making it, it might not make sense. Okay. So, let's say in our body, we have got now 10 grams of a bone. Okay, 10 grams of a bone. Where can I write that? Let me put it on top. Okay, 10 grams of a bone is going to contain 2% of this compound that you're able to see. Now the question is, calculate the mass of hydrogen in a bone. Hope you can now get it. So in the human body, 10 grams uh, contains, I hope you got what I said at the beginning. I might also forget to mention it again exactly the way I'm mentioning it now, so make sure that you get that. So let's say in the human body you have got 10% or 10 grams as the mass of the bone. All right, 10 grams mass of a bone. Now, from this mass of the bone, you know that the bone is going to be composed of a lot of different things. Now, 2% of this mass of the bone is actually this compound that you can be able to see here. Now, we want to calculate the percentage, the mass of hydrogen in the bone. So, this comes from what we call percentage composition. Okay, percentage composition of something is just equal to the mass of that same thing divided by the total mass of the whole compound where that thing is times 100%. So this is how you calculate percentage composition. For example, when you've been given water, okay, in water you want to find the percentage of hydrogen in water. So you know that oxygen, the mass is 16, hydrogen you have got 2, and each the mass is 1, so this is going to give you 18, right? Mean that the percentage composition of hydrogen in water is going to be the mass of hydrogen in water is 2 divided by the total mass, which is 18, and then multiplied by 100%. So this is how you're going to be able to get the mass of hydrogen or the percentage of hydrogen in water. I hope that is okay. I hope that is clear. Now let's work out the question that we have. We have strategically picked it because to introduce it on this topic because I've seen an exam question on it. Since we know that 10 grams of a bone, we have got 10 grams as the mass of a bone. Now from the 10 grams, only 2% is this compound here. Okay, so let's find the mass of this compound in a bone. The mass of this compound in a bone. So we're going to say mass of this same compound NaHO2 is going to be 2% of a bone, right? Which is 2% of 10, because we know that 2% of a bone is actually this compound. So therefore this is going to be 2 out of 100 multiplied by now 10. So a 0 is going to be able to cancel with a 0 there. And so we're going to remain with 2 out of 10, which is 0.2 grams. So what we are seeing is that in a human bone, 0.2 grams is going to be of this compound. I'm not saying this is the true thing, but for this imaginary bone we're talking about, then 0.2 grams is going to be this compound that you're able to see. Now I want to find the mass of hydrogen in this compound. Yes, Martha?
So I've got a question. Is the 10, is it only for the hydrogen or what?
Which 10?
The 10 that's you've written 2 over 100 multiplied by 10. So I'm asking.
This is the mass of a bone. The 10 is the mass of a bone. It's here. the
Oh, then you're trying to find the composition for the hydrogen.
Yes. So you have got a bone, right? This is your bone. It has got a lot of things. It has got a lot of things which is it is made up of. But from all of those things, so this bone has got a mass of 10 grams. From all of those things, a part, one of the components of a bone is this compound. But it is only 2% of the whole bone, meaning that the other parts are made up of different things. For example, calcium and these other things, all right? Do you get that?
I get you, sir.
Very good. So now let's find. First, I'm going to determine the molar mass of this compound. So we know that we have got two oxygen, the molar mass is 16. Carbon, the molar mass is 12. Hydrogen, the molar mass is 1. Sodium, the molar mass is 23. So this is what we need to sum up. 2 times 16 is 32. So that will be 32 plus 12 plus 1 plus 23. That is going to give us 68. This is in grams per mole because it's smaller mass, right? It's measured in grams per mole. So to find the mass of hydrogen, so mass of hydrogen is going to be mass, okay, of hydrogen in the compound, or the composition of hydrogen in the compound. I already wrote that formula, right? So the mass of hydrogen in the bone is going to be actually the molar mass of hydrogen in this compound divided by the molar mass of the whole compound, and then multiplied by the mass of the compound. That is how we're going to be able to find the mass of hydrogen. So the molar mass of hydrogen in this compound is only 1 gram per mole. The molar mass of the whole compound is 68 times the mass of the whole compound is 0.2 grams, right? This is the mass of the whole compound, not a bond, the whole compound where hydrogen is found. So what we are going to see is 1 out of 68 times 0.2, which is the same as 0.2 divided by 68. So we are going to find that the mass of hydrogen in this compound is actually 0.00294 grams. So that's the mass of hydrogen in this compound. So that is how you're able to work it out. Are we okay? Are we good?
But to be honest, you confuse me.
Where are you confused?
How you resulted to. Okay, sir, why did you use the. Okay, I've gotten how you found the answers, but I don't know why you used multiplied by root 2 again. Like after we found the thing.
You have got you have got sodium oxide. Okay, in sodium oxide, this compound has got 2 grams. Now, you want to find the mass of oxygen in this compound. So the mass of oxygen is going to be the molar mass of oxygen divided by the molar mass of the whole compound, sodium oxide. And then you multiply by the mass of the whole compound, sodium oxide. This is what we've done. Are you okay?
Yes, I'm okay. Yes, I'm okay.
Okay, so let's start now with the empirical part, and then we'll go to the molecular part and then get combined with the combustion analysis. So starting with the empirical formula, let's say we have got a compound. I'm just going to be using exam questions since I don't have time to get to construct questions. So let's say we have got a compound that is made up of, let's say we have got 22.26 grams of sodium, and we also have 7.74 grams of oxygen. So we have got a compound which contains sodium and oxygen. Okay, just these two. Now you want to find the empirical formula of this compound which contains these two. There is someone with a question.
Sir, the definition for empirical formula.
It's a simplest whole number ratio formula. A formula that shows the simplest whole number ratio of atoms which are forming a compound. Good?
Okay.
Okay.
Yes. Yes.
So this is the compound that we have. There's another question?
No.
Okay. Now, if you have got a compound which contains sodium and oxygen in this proportion, and you want to find the empirical formula of such a compound, so I'll show you how to just the simple steps to take. So I'll first write element, right? I'll first write element. And the elements that we have got sodium, we have got oxygen. Now make sure that you write them in the order they have given you because you can't have oxygen and sodium reacting like this. Sodium is supposed to be in front there. Okay, and then I'm going to give the mass of each one of these which is given, right? So the mass, this is actually percentage by mass. I can also say percentage mass. So the mass of sodium given, that is the 22.26 grams. The mass of oxygen given, that is 7.74 grams. The next thing that we need to find are the number of moles. And we know number of moles is mass over molar mass. Okay. So the molar mass of sodium, checking from the periodic table, that is a 23. So it's going to be 22.26, divide that by 23. Yes?
Now,
Yes.
why do we use? Oh, I put the past paper where the periodic table has the numbers of moles. So it's better if we use just one and the same thing, like
No.
all the periodic table.
For me, I don't have a periodic table now. That's why I'm using these values because they are simple to know. But make sure that you use the molar mass given on your periodic table. Some periodic tables you find the molar mass of oxygen is 16, others is 15.9,
0.99.
others is 15.9994. But mostly at UNZA you use this. So make sure you use the one they've given you, otherwise you'll be getting wrong things. Okay.
Okay.
Okay, so let's get to divide 22.26 divided by 23. That is going to give you about 0.967826. And then also go to the other part for oxygen. The mass given is 7.7. 7.74. Make sure that the mass is in grams, right? This is in grams, 7.74 grams. Divide by 16. That is going to give you about 0.48375. So you've determined the moles. Now the next thing that you need to determine is the mole ratio. Mole ratio. So you look at these two numbers, which one is smaller than the other? Which one can you say? Mwale, which one is smaller than the other? 0.96 or 0.48?
0.48.
Okay, meaning that both sides, make sure that you divide this one by 0.48, also this one by 0.48. Now you know that 0.48 over 0.48 is itself, right? It's a 1. Okay, that is going to be a 1. And then you go to 0.967826. You divide by the same 0.48. It's going to give you about 2.0006. This is just a 2, meaning that the empirical formula now you can write at the end. Empirical formula is going to be sodium. You have got a 2 down, okay? And then oxygen. We're good? Yes?
Sir, how did that more ratio thingy come in?
So you need to divide by the simplest moles. You look at these moles. By the simplest, that's the one you're going to be able to divide by.
Alright.
Yes. So please, You only round off in some special cases. Trust me, this is going to be trick. If I found 1.5, never round off this. You've learned rational rational and irrational numbers. Make sure that you convert 1.5 into a fraction. If this is what you found, never round off to 2. Never. You'll get it wrong. So let's say the answer that I found here was 1.5, and then here I'd found a 1. So 1.5 converted into a rational, I mean into a fraction, I can say let 1.5 be equal to x, right? And then I multiply both sides by 10 because I've got a decimal here so that it goes at the end here. So we're going to have 10x is equal to 15. Then divide both sides by 10. So mean that x is going to be equal to what? 3 over 2. Mean that 1.5 is the same as 3 over 2. So in a case like this one, I'm going to multiply everything by this number I'm seeing down here, which is a 2. So I'll multiply by a 2. Mean that here we are going to have 3 over 2 times 2, that is just going to give us a 3. And then here will be 1 times 2, that is going to give us a 2. Meaning that the empirical formula would have become n2 with a 3 and then O with a 2. This would be the empirical formula. So take note of that. This is the question that came in that should be 2020 exam. And people were rounding off, getting it wrong. Okay, I hope that is okay. We can have another question that has to do with this. Martha, are you okay?
Yes, I'm trying to understand because it's a bit of noise.
Okay, let's say I've got a compound that has got 38.67 percentage of carbon, and then we have got 16.22% of hydrogen, and then we have got 45.11 percentage of nitrogen. We want to determine the empirical formula of this compound also. So just like we have done on the previous one, just follow the steps. The first one, I'm going to write element. Make sure that you write the elements in the way they've been given, because you don't expect to have carbon bonded to nitrogen and then to, you see, like the order is very important, just the way they've given them. If you And it is important for just to follow the order they've been given. For example, if you don't know which compound is supposed to react with, or which element is supposed to react with which one, so we are going to have carbon, hydrogen, and nitrogen. That's the first thing. And then the next thing, I'm going to write percentage mass. The other one I just wrote mass because that was what was given, but I'll write percentage mass, right? So for the percentage mass for carbon, we have got 38.67. This one, although it's given as a percentage, we're going to take it as mass in grams. And then we're going to have 16.22 grams, which is the percentage also. And then we also have 45.11. If you have a periodic table, you can confirm for me the mass of nitrogen. Is it a 14? If not. And then we are going to find the moles. Let me just check my periodic table for the mass since no one is answering. It's 14? Richard?
Yes.
Okay, good. So let's divide now with by their molar masses to find the moles. So 38.67. The molar mass for carbon, is 12. So divide that by 12. The value that we are going to get is about 3.222. Okay, we go to hydrogen. 16.22 divided by 1. Actually, we know that the molar mass for hydrogen is 1, right? So that will be just 16.22. And then go to nitrogen, we have got 45.11 divided by the molar mass, which is 14. That is going to give us about 3.222. So from here now, find the mole ratio. So you already see that the smallest number that we have here is 3.22. Yes, please.
The formula for finding the number of moles that you're using right now is Mr. over the where are you getting the grams from?
Which grams are we talking about?
The one on top side symbolizes what?
Number of moles is
So
mass
the
over
molar mass,
mass.
where are you getting it?
Molar mass is from the periodic table.
Then the one on top.
The masses are these given, the percentage masses.
So you're using the percentage masses over the molar masses.
Yes.
Okay.
So from here, divide by the smallest number. You can see this is the same as this. So that means that here we're going to get a 1. Even here we're going to get a 1. And then 16.22 divided by 3.22. That is going to give you about a 5. 5.03, which is just a 5. So I mean that the empirical formula for this one is CH5N. Just direct as this, that is going to be the empirical formula. We're good?
Count.
Yes.
Just a minute. I want to write the last question that you given me.
The tutorial video is always there. So,
I've done that tomorrow. Let me just write the last sentence.
right. Which one?
I'm done.
Okay. Now, let's do the combustion analysis part. I'm going to combine it with also molecular formula. Okay. I'm not copying questions, so I'm just writing the values given because I don't have time to copy. Okay. So we've been given naphthalene. Now this compound naphthalene is an organic compound that contains only carbon and hydrogen. What do we call an organic compound that only contains carbon and hydrogen? Anyone? Yes?
They are called hydrocarbons.
Very good. Hydrocarbon. Okay, so we have got naphthalene, which is an hydrocarbon. So on combustion, meaning that you are burning it, right? Reacting with oxygen. So I'm also going to write for you the equation since we know already. So on combustion of naphthalene, so every time they say combustion, meaning that you are reacting with oxygen, and you know that every time you burn an organic compound with oxygen, you are going to form carbon dioxide and water, right? So this is what we have. Now what we've burnt is you have burnt the molar mass. First, we've been given the molar mass of naphthalene, that is 128.2 grams per mole. That's a molar mass. Okay. So again, what you've been told is the complete combustion of this compound is going to produce 69 grams of carbon dioxide. 69 grams of carbon dioxide, and it is also going to produce 11.3 grams of water. Right? Now the question is find its empirical formula and also its molecular formula. It's an interesting question. I like this question very much. So let's find the empirical formula, and please, for combustion analysis, if you just follow the method I'm giving you, will never go wrong. Okay. You have bent this organic compound. Actually, I don't need to know the formula. If I didn't even know the name, I would have just put X. Okay, so you burn it in oxygen, you form 69 grams of carbon dioxide and 11.3 grams of water. Now I want to find its empirical formula, its molecular formula. So the first thing that we are going to do, look at this carbon dioxide you have here. So let me ask, if you have got 1 mole of carbon dioxide, how many moles of carbon do we have in this compound? In other words, when you have got 1 carbon dioxide, how many carbons do you want to have? How many carbons are going to form 1 carbon dioxide? Are we moving together?
Isn't it
Sir,
Monica?
it started breaking. What did you say?
Okay. If you have got one carbon dioxide, how many carbons are there? That's my
One.
It's one, right? Very good. So this is just telling you that one mole of carbon dioxide is equal to one mole of carbon. So mean that the number of moles of carbon dioxide is equal to the number of moles of carbon. Okay, just a moment. Are you sure it has gone? You all can't say. Pardon? You can see now?
Yeah, we cannot see.
Okay. So what I'm saying is that one mole of carbon dioxide contains one mole of what? Of carbon. Now, we have got laws of stoichiometry, and one law is the law of conservation of mass. The mass on the reactant side is going to be equal to the mass on the product side because mass is not formed nor destroyed.
So are you writing anything right now?
I'm not writing, I'm speaking. Okay. Can you get?
Yes, I can get you.
Okay. So what I'm saying is that the mass on the reactant side for any element should be equal to the mass on the product side. So the only point where we have got a carbon is here and an hydrogen is here. So if only naphthalene contains carbon and hydrogen, meaning that the O of the carbon which was on the on the reactant is this carbon that you can see on the product. And the O of the carbon that was on the reactant is this carbon that you can see on the product. So if you find this number of the carbon, the mass of carbon on the product, that is the same mass of carbon which was on the reactant. And if you find the mass of hydrogen on the product, that is the same mass of hydrogen which was on the reactant side. So that is basically what we are saying. Are we okay?
Okay, though it broke. It was breaking.
I hope you can. I hope it's okay now. Okay. So now who can tell me, since we've already been given data here, how can we find the number of moles of carbon dioxide? Anyone?
Mass over molar mass.
Mass over molar mass, right? Okay. The molar mass of carbon dioxide is what? So,
It's 12.
so carbon dioxide, we have got two oxygen. The molar mass is 16. I'm using 16, but please use the one from the periodic table will be given, and this is 12. So 2 times 16, 32. 32 plus 12, 44. So that's the molar mass of carbon dioxide. Meaning that the number of moles of carbon is going to be mass of carbon dioxide, okay, mass of carbon dioxide over molar mass of carbon dioxide. Mass of carbon dioxide given is 69. Molar mass of carbon dioxide is 44. So what are we finding as the number of moles of carbon? 69 over 44. 1.568 moles. So this is the number of moles of carbon. Yes?
Yes, sir. As in, on the mass, which is 69 grams, is it not for both carbon? Is it not for carbon dioxide? As in, how is the carbon bearing the same mass?
They, they are not bearing the same mass. I found the number of moles of carbon dioxide by saying mass of carbon dioxide over molar mass of carbon dioxide. Now the number of moles of carbon dioxide is the same as the number of moles of carbon. That's why I've equated them.
Or is it because of the thing that said that one more of carbon is just the same as one more of carbon dioxide?
Yes.
Okay.
Okay, good. Is there another question? Okay. Let me also find. So these are the number of moles of carbon. Let's also find the number of moles of O. Now let me ask. How many moles of hydrogen are going to be equal to one mole of water? Or what is the relationship between a mole of water and a mole of hydrogen in a water molecule? Who can answer us for that? What's the relationship between the number of moles of hydrogen and the number of moles of water in a water molecule?
Like in carbon dioxide, I'm very sure.
You are sure?
Yes, yes.
So who is sure to answer me?
Like there are two hydrogens in water.
Okay.
Like two moles of hydrogen.
Okay. Let's say if you have got one mole of water, how many moles of hydrogen do you expect? One mole of water. How many moles of hydrogen do you expect? Or maybe let me say, if you have got 2 moles of water, how many moles of hydrogen do you expect here?
I expect four.
Very good. You expect 4 moles of hydrogen, right? Hydrogen. Very good. So this is just telling you that the number of moles of water, multiply it by 2 to get the number of moles of hydrogen. Okay? So number of moles of hydrogen in water is equal to 2 number of moles of water. This is coming from the fact to say number of moles of hydrogen divided by this comma subscript is equal to number of moles of water divided by the number in front of water, that is a 1. But you end up crossing and multiplying. That's why the 2 which was on the denominator goes there. I hope we are good. So now let's determine the number of moles of hydrogen. Number of moles of hydrogen is going to be 2. How do you find number of moles of water? It is mass over molar mass. So the mass of water is 11.3. The molar mass of water is 18, right? It's 18. And so we'll say, of course, the 2 can go into 18 9 times. So we have got 11.3 over 9. What's the answer? That's 1.25.
1.25.
Okay, good. Now I've already determined the number of moles of carbon and the number of moles of hydrogen. So we can now go on and determine the formula, the empirical formula. Since we know that naphtha only contains these two, alright, it is an hydrocarbon, meaning that it doesn't have any other compound apart from what I've written. So I'm going to write element. So for the elements we have got carbon and hydrogen in naphthalene. And then I'll just go direct to the moles because the others we've already done. The moles for carbon is 1.568, for hydrogen is 1.255. Okay, and then more ratio. So we'll divide by the smaller number. You can see the smaller number is 1.255. This is going to be 1. And then we also get the 1.568. Okay, we divide by 1.25. That is going to give us about 1.24. 0.89. Now for a number like this one, you can simply round off, meaning that the mole ratio is 1 to 1. Meaning that the empirical formula of this compound is CH. Okay, is CH. And then to find the molecular formula, yes, we have a question.
For carbon dioxide and the water, how come you found that the solutions for for carbon dioxide you gave them to carbon, then the solutions for water you gave them to hydrogen?
So you haven't been following all this long.
I have been following, but I was wondering how you are going to separate the carbon alone, because the carbon we should find for the carbon alone and for the hydrogen alone. Then we just found for everything for carbon dioxide, then decided to give the same thing to.
Those are
We
questions should
just
be asking when I'm solving, not when I've reached this far. You are going to understand on the next question. So the molecular formula is given by empirical formula multiplied by n. Now this n is the value that we need to determine. And you can't determine n if you don't know the empirical formula. So n is given by molecular formula mass divided by empirical formula mass. Empirical molecular formula mass is this mass, the molar mass that you've been given, or we can just say molar mass divided by the empirical formula mass. That is 128.2 divided by the empirical formula mass. So you look at the empirical formula. Carbon has got a mass of 12, hydrogen a mass of 1, so that is 13. So that's how you determine m. So that is 128.2 divided by 13, and that is about 9.8, which is basically 10. Okay, 9.8. So get your own number. So meaning that the molecular formula is going to be, empirical formula is CH, and then where there is N you are going to put 10. So therefore the molecular formula is going to be C10H10 there. Oh, okay. Are we good? Are we good? Okay, let's look also at this question. Also for this one we've been told upon combustion a hydrocarbon, so we also have an hydrocarbon, so let me call it X. We know that is upon combustion, meaning that what will be the product? What will be the product?
Carbon dioxide and water.
Okay, carbon dioxide and water. So upon combustion of this hydrocarbon, we produce 25.15 grams of carbon dioxide, 25.15 grams of carbon dioxide, and 11.58 grams of water. So the molar mass, or the molecular form, the molar mass of the hydrocarbon also has been given as 114 grams per mole. So the question is determine the empirical formula and the molecular formula. Now, if you didn't understand, I don't want to change formulas. I think the one I mentioned was just simple. Okay, I'll stick with that one. So we are saying for every 1 mole of carbon dioxide, you have got 1 mole of carbon. Mean that the number of moles of carbon are equal to the number of moles of carbon dioxide. Okay, so if I find the number of moles of carbon, automatically I found the number of moles of carbon dioxide. If I found the number of moles of carbon dioxide, automatically it is equal to the number of moles of carbon. So how do you find the number of moles of carbon dioxide? It is the mass of carbon dioxide over the molar mass. Okay, so the mass of carbon dioxide is 25.15. The molar mass is 44. I hope we are following. So actually, okay, I'm going to use that. Has someone punched that? So this is going to give us number of moles of carbon dioxide, which is equal to number of moles of carbon to be 0.57159 moles. Martha, are you okay? And we have said the number of moles of hydrogen is twice the number of moles of water, because if you have got one water molecule, it means you have got two hydrogens, so the number of moles of hydrogen is twice the number of moles of water. So the number of moles of hydrogen is going to be 2. Number of moles of water is mass of water, which is 11.58, over the molar mass of water, which is 18. So basically this is just 11.58 divided by 9. And so this is going to give us about 1.2866. Yes, please.
The 11.58, how is it coming about?
It's here.
Okay.
Okay. So we have determined the number of moles of carbon dioxide and the number of moles of, carbon and hydrogen. So now write here element. I'm going to put carbon and then hydrogen, and then we are going to have the moles. Okay, for carbon we have got 0.57159. For the other one we've got 1.2866, and then we need to find the mole ratio. So this number 0.57 is smaller than 1.2, so divide both sides by the same 0.57. So here it will give us 1. Then 1.28 divided by also the same 0.57, that is going to give us about 2.25. First, are we good up to here?
Yes, sir.
Okay, now when you find, of course I've not found exactly 2.25, I found 2.25 with some things. Yes, please, there's a question. Does anyone else have a question? Now, I've not found exactly 2.25. I found 2.251 with some other things. But because it ends in 25 or point 0.5, so those are some special cases where you need to find, to convert that into a fraction. Okay? So I'm going to say let x be equal to 2.25 multiply by 100. So 100x is going to be equal to 225. Divide both sides by 100. X is going to be 225 over 100. Let's see this one in the simplest form as a fraction. What number can go into both without leaving a remainder? Let me see what.
25.
25. So what are we going to have?
45 over.
So this is approximately equal to 9 over 4, right? It's 9 over 4 if you convert it as a fraction. You simplify this fraction here. So meaning that you are going to multiply by a factor. That's the next step. Multiply by the thing in the denominator, which is 4. So we're going to have 1 times 4, which is going to be 4. 9 over 4 times 4, that is going to be 9. Mean that empirical formula then is going to be carbon 4, hydrogen 9. This is the simplest one number formula. Yes.
So sir, like for example, the same thing that we found there after dividing is giving something that is terminating decimal. So now
Uh-huh.
when you have a terminating decimal, you have to what's is to multiply it by hundreds
No,
according to the decimal place what
for a terminating this
position.
for a terminating decimal, when you are converting it into a fraction, you don't multiply. You use all those rules for converting a rational number into a fraction for a terminating decimal. I mean for a non-terminating decimal or a repeating number.
Okay.
Yes, Martha.
So for the 9/4 that you had to put the bigger one on that one, the number which was big, and then for the 4 you have to look for the one which was small. You just got to easily putting it.
No, you actually, it should be the same number that can go into 20, 225 and 100. You'll be using a calculator, so just punch on your calculator 2.25, and then there is a part which is written, is it AB over C? Press there. It will convert this number into a fraction, just on your calculator.
Yes, but I don't get how you found the 9/4. Like where there is carbon, you put there 4, and then where there is hydrogen, you put 9. I'm asking, did you just put the
Have you seen this statement?
yes?
Multiply by 4. So you are multiplying everything here by 4. Okay. So this is going to be the empirical formula. We can now determine the molecular formula. Now to determine, yes, yes, Richard.
What the minimum value for your notebook, which is rounded to the
Uh,
level,
there's no minimum. You can,
is rounded to the decimal.
yeah, there's no minimum. You can round off on anything, but there are special cases which you consider when something is ending in point 0.5, in 0.25. These are some special cases that you are not going to be able to round off. Okay, or something is ending in 0.67 or 66667, like it's a repeat. Those are some special cases where you don't round off but you get to convert into a fraction. Is that okay?
Sir,
Yes.
I'm asking. I'm not clear. Why did you multiply by 4? It broke a bit.
you
It
you
was
you,
breaking.
you watch.
So I don't have bundles.
Are you sure you are lying?
I'm not lying.
Okay, so you multiply by 4 because we converted the other one, it gave us a fraction, right? It gave us a fraction. The other part which we had gave us a fraction, 9 over 4. So we didn't want a fraction. So the same thing which is in the denominator, since it was 9 over 4, multiply everything by the same thing which is in the denominator, which is a 4.
Okay, thank you.
Okay. So let's find the empirical formula mass. So you get the empirical formula, you find its molecular mass. So that's what we call empirical formula mass. 4 times 12 is 48 plus a 9. That is a 57 grams per mole. So to find the value of n is given by the molar mass divided by the empirical formula mass. So the molar mass is 114, empirical formula mass is 57. Now the periodic table that I'm using is the one which is giving me these values, meaning that I can be finding also some wrong things because I'm using rounded off values. So the periodic table that I'm going to give you will be specifically for this. So 114 divided by 57 has given me exactly 2. So you see how it's giving exactly. So a periodic table that they'll give you. So if you didn't multiply by that, you would have gotten n to be something very big. Okay? If you didn't multiply by 4, or if you just rounded off the value that you found. So I mean that the molecular formula is going to be empirical formula multiplied by n. The empirical formula is C4H9, and then n is 2. That the molecular formula is going to be C8H, sorry, not, is that 8? Okay, that's true. H18. That is it. Are we together, friends? Are we together? Yes.
So where did you get that 114?
114. It has been given in the question. That's the molar mass of the compound. They've not given you.
Okay.
Any other question? Any other question? Okay, let me now look at the last example. Then we are done with this topic. So the me giving all these examples is meaning I don't want anyone to get wrong anywhere. So I'm going to bring a test or a quiz from the beginning. Now for this one, X is not an hydrocarbon. So they've told us combustion analysis of, they've actually given us a mass of 28.4 grams of an organic compound which contains carbon, hydrogen, and oxygen, produces 54.3 grams of carbon dioxide and 15.6 grams of water. Find the empirical formula of the compound. So I've not been given the molecular formula, I've just been given the mass of that compound. Now this one doesn't contain carbon and hydrogen only, but also oxygen. Okay, can we go with it? Are we together? Okay. Can someone give me the relationship between the moles of carbon and the moles of carbon dioxide?
Go.
Pardon? Can you say that again?
The most of
Yes? The moles of carbon are equal to the moles of carbon dioxide, right? Are we moving together? This is the last question, please. So make sure that you,
yes.
okay.
Okay, sure.
And then the moles of carbon dioxide is given by what? Mass of carbon dioxide, which is 54.3, over the molar mass of carbon dioxide, which is 44. Okay, that is going to give us what? 54.3 divided by 44. That is about 1.23409. These are the moles of carbon dioxide, which is as well the moles of carbon. Now, for such a question like this one, because we also have oxygen, these moles of carbon are found. I'm going to convert them to mass of carbon. How can I find mass given the number of moles? How can I find mass?
Its mass is equal to number of moles times molar mass.
Good. Number of moles times molar mass. So the number of moles I've already found 1.23409 times the molar mass. I'm finding the mass of carbon, not carbon dioxide. So the molar mass of carbon, that is 12. So multiply this value by 12. That is going to give us about 14.809 grams of carbon. Okay, the next thing that I'm going to do is to determine the number of moles of hydrogen, which we know is twice the number of moles of water. So this is going to be equal to 2 number of moles of water is mass of water, which is 15.6, divided by the molar mass of water, which is 18. Right? So this is basically 15.6 divided by 9. And this is going to give us 1.733 grams of hydrogen. Sorry, not grams, but moles of hydrogen. We also need to find the mass of hydrogen. So mass is still number of moles times molar mass. So this is going to be number of moles is 1.733 times the molar mass of hydrogen is a 1. I'm using 1, but you can use 1.008 or 1.007984. So that will still be 1.733. Now this is going to be grams of hydrogen. Now what is remaining is for us to find the mass of hydrogen. So to find the mass of hydrogen, for the mass of hydrogen, I'm not going to use this formula I've used to find the mass of carbon and hydrogen. I mean to find the mass of oxygen. I will not use this formula. The reason is simple. You have got on the reactant, we didn't only have this oxygen, okay? We also had this oxygen. Actually, also on the product, we've not only formed one oxygen, we formed this oxygen and this oxygen. Okay, now for carbon and hydrogen, the same carbon which is here is the same carbon that you can see here, meaning that this mass that you are able to see is the same mass that came from the reactant. Also hydrogen, you can only see it once on the reactant and once on the product, meaning that the same mass that you are able to see on the product for hydrogen is the same mass which was there on the reactant. So to find the mass of oxygen which is on the reactant is going to be the mass of the whole compound because it only contains these three, right? So that is 28.4. You remove the mass of carbon, okay, which is 14.809. Also remove the mass of hydrogen, which is 1.733. So that will give you the mass of oxygen. Are we good? Are we moving together, dears?
Yes.
Okay, so that will give us 11.857666 grams. Now let's also convert these grams to mass. I mean to moles, right? To moles. So number of moles now of oxygen is going to be mass over molar mass. The mass given is 11.857. The molar mass of oxygen is 16, right? So this is just divide this value by 16. That would be about 0.7411 moles of oxygen. Now we can determine the empirical formula. We know the moles of carbon, the moles of hydrogen, and also the moles of oxygen. So I'll write element. So carbon first, hydrogen, and then oxygen. I'll go direct to the moles. For carbon, that is 1.23409. Hydrogen is 1.733. Oxygen is 0.7411. Which one is the smallest number here which we are going to divide everything through by? For oxygen. So meaning that here we're going to get 1 because we're going to divide by itself. And then for the rest, we'll say 1.23409, divide that by 0.7411. That has given me about 1.665. And then go to the other one, which is 1.733, divide also by 0.7411. 7411, that is going to be about 2.338. So for this one, if this was giving me a 7, I would have said, okay, maybe it was repeating, like 1.667, maybe it was repeating. So the way it is, I can say this is approximately equal to 1, this is approximately equal to 2, this is just a 1. So I mean that empirical formula for this compound is CH2O.